Hi, we are Group 6 and we're presenting our project for the CZ4041 machine learning module. For our project, out of all the available projects listed, we have chosen the Zindi Afridca challenge hosted on the Zindi platform. We'll be first going through the problem statement and the challenges of the project, followed by sharing the exploratory data analysis, feature engineering, then moving on to the methodology, which we'll be sharing about the models used for our project, then concluding with the takeaways we had. Let us begin with the introduction to the problem. As female-headed households are becoming increasingly prevalent in South Africa, the objective of this challenge is to make use of machine learning to build a predictive model that accurately estimates the percentage of households per ward in South Africa that are female-headed and living below a certain income threshold. This solution will be crucial to help local government make policies pertaining to poverty issues in South Africa and better support these households. Here are some of the challenges of the problem. Firstly, the features provided in the dataset includes an unusual feature, ADM4 P code, which is the ward code used to find the ward polygon in the shapefile provided. For the feature and some other features, we had to use other external APIs or conduct further processing and conversion before they could be used. Secondly, we faced some troubles coming up with good engineering features, as most of the ideas we thought did not improve or had very little implication on the scores. As such, we had to explore more different variations as well as combination of engineering new features. Moreover, one of the most challenging problems we faced was the fact that there was no correlation between local cross-validation and the leaderboard. Hence, it was challenging for us to evaluate how good our model is performing and whether it was overfitting until we made the submission. Besides that, it was difficult to climb the leaderboard as well. Next, we will move on to the EDA of the dataset. The dataset is already divided into train and test dataset, with 62 features in total, 2,822 rows in train dataset plus the target variable, and 1,013 rows of data in the test dataset. The dataset contains information such as percentage of dwelling type, percentage listing that has present school attendance, percentage with piped water access, satellite TV, and so on, as well as the target variable, which is the percentage of women-headed households with income under a certain number. This is also what our regression problem aims to predict. We investigated the correlation between the different variables and the target variable using the dot correlation function and plotted a confusion matrix. From this snippet, as shown here, we can see that there were rows with NaN values, which is null values. In total, there are 5 features of which the values are all 0. We also used FitEXP to identify the usefulness of the features. This is an example of the variable PSA00 showing a high correlation trend of R equals to 0.782. And this is an example of the variable LAN08 showing a low correlation trend of 0.004. As there are many features to take into consideration, we also performed a regressive correlation analysis to select the important features. Essentially, a linear regression was first performed with all the 62 features included to obtain the root mean square error, which determines the baseline RMSE. Then we proceed to use the ranked correlation features and drop them individually, and linear regression was performed again on the subset of features to obtain the new RMSE. The feature which was important will cause the RMSE to increase, while the features which are not so important will cause the RMSE to decrease when dropped, since the model performs better without the feature. From this graph, you can see that the RMSE dropped the most when the top 9 correlated features are dropped, which means that the model performs better without these 9 features. As such, we dropped these top 9 lowest correlated features, as well as removed redundant data such as the 5 features with zeros, as elaborated earlier.
Next, we'll be talking about feature engineering. Binning was done on 4 groups of features: pipe water, population group, education, and luxury, as it was hypothesized that the merging of similar subcategories may reduce the number of features present and improve model performance. For pipe water access, 2 binning methods were being done. The first one, a binary feature of whether individuals had pipe water access, and the second, which categorizes pipe water access based on the location in the house, outside the house, or no access. The differences in RMSE were not significant and showed that binning should not be performed. For population group, we hypothesized that the skin color of an individual may have an influence on the income level of an individual. But after performing binning to separate individuals based on these categories, Black Africans, people of color, and individuals who are neither Black Africans nor people of color, the RMSE increased slightly. For education, individuals were grouped based on people with present school attendance, people without present school attendance, and others. However, the RMSE did not improve. Individuals were also grouped according to the presence or absence of luxury items such as cars, satellite TV, and landlines. Adding this feature resulted in a marginal improvement in RMSE. The binning method did not work and showed that individual features play a crucial role in model prediction. The features may not have done well with binning, as some of the individual features had conflicting trends. This caused greater inaccuracies with respect to prediction. New features were generated to complement the pre-existing features in the dataset. Family is a new feature that tells us the number of individuals in a household. This is potentially useful as larger families may be less well off due to more expenditure required to support members in the family. Two other features, clusters and geolocation, are generated from the latitude and longitude data. This is because individuals who live in the same area may have similar financial outlooks. Clusters is a feature that is generated using k-means clustering via the use of coordinates data. The optimal number of clusters is determined by the sum squared error, while geolocation uses a reverse geocoder to obtain more information on the nearest cities, towns, and country code, which serves as additional categorical features that can be converted into suitable inputs via one-hot encoding to improve model performance. Next, we perform the rounding of float features. As features such as nightlight, family, total households, and total individuals are intuitively variables that are integers in nature. To ensure the theoretical accuracies of these features, the values of these features are rounded to the floor of the integer or nearest 10th digit. The rounding of family, which is the number of individuals in a household, resulted in the largest reduction of RMSE of 0.046.
Now we'll move on to the methodology. Based on the process dataset, we explored individual models' performance on the regression task. K-nearest neighbors was used as one of the individual models. It predicts target values based on the values of its surrounding neighbors. For regression, prediction is done through local interpolation of the points associated with the nearest K neighbors. This is the initial model that we use, where all the parameters used are the default ones offered by scikit-learn. This will be considered as the baseline benchmark for hyperparameter tuning. To do hyperparameter tuning, the grid search CV method was used, and it performed an exhaustive search over the set of parameters specified here, which are the neighborhood size, the weighting scheme for each point, and the algorithm used to compute the nearest neighbor. The optimal parameters that were found are shown at the bottom. The results and rankings will be shown in the next section. The next model explored is the random forest. It fits multiple decision trees on a given dataset and averages over the decision trees to improve accuracy and reduce the chances of overfitting. This is the initial model that we used. Similar to k-nearest neighbors, all the parameters used are the default ones offered by scikit-learn. The parameters that underwent tuning were the number of trees, maximum depth of each tree, and the criteria for how good a split is. The optimal parameters found are shown at the bottom of this slide.
So next we have the support vector regression, which is essentially the support vector machine. This aims to fit an appropriate hyperplane to the dataset, while also maintaining a certain level of tolerance for error due to regression. So this is the baseline model that we used, where once again, the parameters were set to default. The parameters C and epsilon were subjected to tuning. C is the regularization parameter, and epsilon is the margin of tolerance. The optimal parameters can be seen here. XGBoost is an open source gradient boosting algorithm, which corrects predictive errors made by previous models. The gradient descent optimization algorithm and a loss function is also used to fit the model. The algorithm that we used was from the scikit-learn API. Initial testing of the model with these parameters gave poor results, with a Zindi score of 4.39. Grid search CV was then used to find the optimal parameters. It was set to 5-fold cross-validation, and mean squared error was used to find the optimal parameters, which are listed here. LGBM is another popular gradient boosting algorithm. LGBM employs three techniques: GBDT, which is the traditional gradient boosting method, GeoSS, which excludes a significant portion of the data, and EFB, which puts mutually exclusive features together. So we went straight to parameter tuning for the LGBM model. Once again, we used the grid search CV. The 5 folds were fitted for 192 parameter variations, leading to 960 fits. The optimal parameters were found to be the parameters shown on the screen. The next model that we have is CatBoost, which utilizes a variant of ordered boosting. CatBoost also builds symmetrical trees, as leaves from a previous node are split on the same conditions. This allows for faster CPU implementation, which leads to decreased prediction time. The cat-boost regressor that you see here is from the scikit-learn API, and these were the initial values that we used to run the data with. As you can see, the score from the initial model was not ideal. Grid search CV was fitted for 64 parameter variations, leading to 320 fits. The optimal parameters was found to be those listed on the screen here.
To improve our scores, we also tried ensemble stacking. Stacking is an ensemble method where the predictions of a model are used as features for another model. In our case, we used the VecStack library due to its straightforward APIs and full compatibility with scikit-learn. There were 3 main experiments conducted. The results of these experiments will be shown and explained in the later section. Our first approach was an all-in approach where 8 models were included in the ensemble. We then decided that it was better to use fewer models, but use models with better performance. Hence, 3 models were picked: cat-boost, XGBoost, and random forest, and stacked together. The order at which they were stacked was changed iteratively, and the choice of final estimator was varied as well. This resulted in us having 18 models in total. For the final estimator, we discovered that cat-boost resulted in the best performance, while XGBoost resulted in the worst performance. Lastly, to improve our results, we decided to reduce the number of models even further, leaving only the cat-boost and XGBoost models in the stacking ensemble. Now we will talk about our results, some of our novel ideas, and give some concluding remarks for this project. These are the scores for the individual models described earlier on. Note that the scores shown are after performing hyperparameter tuning. From the scores, we can see that k-nearest neighbors resulted in the worst performance amongst the individual models, while cat-boost resulted in the best performance, giving a rank of 79 out of 197. For the stacking ensemble, the approach where 8 models were included resulted in a rank of 179 out of 197. The models used are as listed. For our next experiment, cat-boost, XGBoost, and random forest were picked and stacked together. This gave us a rank of 78 out of 197, which is an improvement, but still not good enough. However, this shows that using fewer models of better performance worked. Hence, we removed the random forest model from the ensemble as it had the worst performance amongst the 3 models and fitted the ensemble to the training data again. This time, we obtained a rank of 45. Using our best performing model, we obtained a score of 3.6054 on the Zindi competition platform. Hence, our rank is 45 out of 197 participants, which places us in the top 22.8%.
So here are our novel ideas. Instead of jumping straight into training a state-of-the-art model without modifying our dataset, we did an initial data exploration to better visualize and determine the best steps to take to pre-process our data prior to training our model. This allowed us to drop the features that would not contribute to building a good model. Additionally, we carried out data processing like reverse geocoding. Through reverse geocoding, we were able to obtain the country code and administrative location data of various wards from the latitude and longitude information given, which allowed us to engineer more useful features. Additionally, hyperparameter tuning was also carried out using a grid search method, and this allowed us to improve the quality of our model in a more automatic fashion. For the stacking ensemble, we also explored the effect of stacking order and choice on our final estimator on the quality of the model, where we discovered that using cat-boost as the final estimator gave a significantly better result as compared to other models. So these are our key takeaways for the project. Firstly, exploratory data analysis allowed us to identify features that do not contribute to the model's performance and eliminate them. Although this might not have made a huge contribution to our final results, it has reduced the complexity of the computations through dimensionality reduction. Moreover, exploratory data analysis also allowed for the better visualization and understanding of the dataset, which helped in the next step of feature selection and engineering. Next, we have the feature engineering, which caused a significant improvement in our results, as we made use of all the given features to engineer meaningful data. Although most of our experiments did not end up improving the model, it was through these that we discovered some meaningful engineered features. Additionally, different machine learning models and algorithms are suited for different problems. In our experiments, we witnessed jarring differences between the performances of various ML models due to the nature of our task. For example, KNN did not perform well as it was meant for clustering problems, while SVM did not perform well as our data was not easily segregatable by hyperplanes, and we had a large number of features which were not highly correlated with the target variable. Nevertheless, it was through this that we learned that there is no single best model that suits all problems. The performance of different methods will depend heavily on the context and nature of data. So this slide here shows each of our contributions. And with that, we've come to the end of our video presentation. Thank you.